On October 13th, 2024, SpaceX did something that defied every principle of rocket engineering we've held for 70 years. They launched a rocket taller than the Statue of Liberty, sent it to the edge of space, and then caught it with giant mechanical arms as it fell back to Earth at supersonic speeds. The engines were still glowing red hot. The metal was groaning under stress, and in that single moment, the entire timeline for getting humans to Mars just accelerated by decades. This wasn't just an engineering achievement. This was the moment spaceflight changed forever. To understand why catching a rocket changes everything, you need to understand the single biggest problem in space exploration: the rocket equation. It's a mathematical prison that has trapped every space program since the 1950s. Here's how it works. To lift just 1 kilogram of cargo to orbit, you need approximately 20 kilograms of fuel. But here's the problem. That fuel itself has weight, so you need more fuel to lift that fuel, which adds more weight, which requires even more fuel. It's an exponential cascade that spirals out of control. By the time you've built a rocket capable of reaching Mars, roughly 90% of its total mass is nothing but fuel. Only 10% is the actual rocket structure and the cargo you're trying to deliver. And here's the cruelest part of all. Traditionally, after each launch, you throw the entire rocket away. Every engine, every fuel tank, every piece of precision engineering, gone. The Saturn V rocket that carried astronauts to the moon cost $63 million per launch in the 1960s. Adjusted for inflation, that's over $500 million in today's currency. And after each mission, every single component ended up at the bottom of the Atlantic Ocean. This is where SpaceX completely rewrote the rules of spaceflight. In December 2015, they achieved what the entire aerospace industry said was impossible. They landed a Falcon 9 booster vertically, right back on the launch pad it had lifted off from just minutes earlier. The rocket had launched, climbed to the edge of space, delivered its payload to orbit, and then turned around and fired its engines in reverse to come back down. Landing a rocket vertically requires extraordinary precision. You're trying to balance a 15-story building on a column of fire while it's traveling hundreds of miles per hour. The slightest error in thrust or angle, and the whole thing topples over and explodes. But SpaceX figured it out. The aerospace establishment had claimed that the fuel required for landing would make the whole system too heavy to be economically viable. They said you'd spend so much propellant on the landing that you'd have no payload capacity left. They were wrong. SpaceX proved that by reserving about 15% of the fuel for landing, you could recover the most expensive part of the rocket and use it again. But here's the thing most people miss. Landing a Falcon 9 was groundbreaking, but it's still not nearly enough for Mars. The Falcon 9 can carry about 17 tons to low Earth orbit. That's perfect for launching satellites and sending cargo to the International Space Station. But Mars isn't just up in orbit. Mars is an average of 140 million miles away, and that distance varies depending on where Earth and Mars are in their orbits. Getting to Mars requires carrying not just cargo, but also all the fuel you'll need for the return journey, plus everything required to keep humans alive for the 6 to 9 month voyage. You need a fundamentally different scale of capability. You need a rocket that can carry not 17 tons, but over 100 tons. And critically, you need to be able to launch that same rocket 10, 15, maybe 20 times in rapid succession to refuel it in orbit before it departs for Mars. This is where Starship enters the picture, and everything changes. Starship isn't just a bigger version of Falcon 9. It's a complete rethinking of what's physically possible in spaceflight. Let me give you the numbers because the numbers are genuinely staggering. The entire Starship system stands 121 meters tall. That's nearly 400 feet, taller than the Statue of Liberty, including its pedestal. When fully fueled, the entire stack weighs 5,000 metric tons. That's the weight of a naval destroyer. The first stage, called Super Heavy, is powered by 33 Raptor engines. 33 separate rocket engines, all firing simultaneously. To put that in perspective, the Space Shuttle had 3 main engines. The legendary Saturn V had 5 engines on its first stage. Super Heavy has 33, and each individual Raptor engine produces more thrust than any of the engines on those historic rockets. When all 33 engines ignite together, Super Heavy generates over 16 million pounds of thrust at liftoff. That's twice the thrust of the Saturn V, which held the record as the most powerful rocket ever successfully flown for over 50 years. The ground literally shakes for miles when this thing launches. But raw power isn't what makes Starship revolutionary. What makes it revolutionary is that it's designed to be completely and rapidly reusable. Not partially reusable like the Space Shuttle, where you had to practically rebuild the engines and replace thousands of thermal protection tiles after every single flight. Completely reusable, both stages. The Super Heavy booster lands back at the launch tower where mechanical arms catch it out of the air. The Starship upper stage can land anywhere you need it to, whether that's back at the launch site, on the Moon, or on the surface of Mars. And the goal is to turn these rockets around and launch them again within hours, not months. Now let's talk about what this means economically, because this is where everything truly changes. NASA's Space Launch System, the rocket that's supposed to take us back to the Moon, costs approximately $4 billion per launch. $4 billion, with a B, and it's completely expendable. You use it once and it's gone forever. The SLS can carry about 27 tons to lunar orbit. That works out to roughly $150 million per ton of cargo. Now, compare that to Starship. According to SpaceX's projections, once Starship is fully operational and rapidly reusable, the cost per launch could drop to as little as $2 million. $2 million versus $4 billion. That's not just an improvement, that's a reduction of 99.95%. Even if those projections turn out to be wildly optimistic, and the real operational cost ends up being 10 times higher than projected, you're still talking about $20 million per launch versus $4 billion. And Starship can carry over 100 tons to low Earth orbit. Let's do the math on that. At $2 million per launch carrying 100 tons, that's $20,000 per ton. Compare that to SLS at $150 million per ton. Starship could be 7,000 times more cost-effective per ton of cargo delivered to space. 7,000 times. This isn't an incremental improvement. This is the kind of paradigm shift that changes what's possible. Suddenly, missions that were economically impossible become feasible. You're not choosing between sending a small rover or a large rover to Mars. You're choosing between sending a habitat module or sending 10 habitat modules for the same price you used to pay for one. But here's the critical piece that makes all of this possible: orbital refueling. You can't just launch Starship directly to Mars from Earth's surface. The rocket equation won't allow it, even with Starship's massive size. The solution is elegant but complex. You launch the Mars-bound Starship into Earth orbit with empty fuel tanks. Then, you launch multiple tanker Starships, one after another, each carrying nothing but fuel. Each tanker docks with the Mars ship and transfers its propellant. Current estimates suggest you'd need somewhere between 8 to 14 tanker flights to fully refuel a single Mars-bound Starship. That means launching the same rocket booster 15 times in rapid succession. The booster launches, lands, gets refueled, and launches again, over and over. This is why catching the booster with mechanical arms changes everything. The old method of landing on legs caused stress fractures in the rocket structure. Those legs had to be inspected, refurbished, sometimes replaced. The catching mechanism eliminates that entire problem. The rocket never touches the ground. It goes from flying to captured to ready for the next launch. SpaceX's goal is to turn around a Starship booster in under an hour. That's faster than most commercial airlines turn around a passenger jet. And this isn't science fiction anymore. They've already caught the booster. The technology works. Now, it's just a matter of scaling it up and proving the rapid reusability. So what does an actual Mars mission look like with this system? Let's walk through it step by step because the architecture is genuinely brilliant. First, you launch a cargo Starship to Mars during the optimal launch window. This happens every 26 months when Earth and Mars are properly aligned. This cargo ship carries everything you'll need on the surface: solar panels, life support equipment, a mining rig to extract water from Martian ice, a chemical plant to convert that water and Mars' carbon dioxide atmosphere into rocket fuel, construction equipment, spare parts, food supplies, everything. It lands on Mars and immediately begins setting up infrastructure. The chemical plant starts producing methane and oxygen propellant using Martian resources. This is called in situ resource utilization, and it's absolutely critical. You're not carrying return fuel from Earth, you're making it on Mars. 2 years later, during the next launch window, you send the crewed Starship. By the time humans arrive, there's already fuel waiting for them. Habitats are partially set up and systems are operational. The crew lands, conducts their mission for the next year and a half until the return window opens, and then flies home in the same Starship they arrived in, fueled by propellant made on Mars. But here's what makes Starship different from previous Mars plans. You're not sending 4 astronauts in a tiny capsule. Starship's pressurized volume is over 1,000 cubic meters. That's bigger than the entire International Space Station's pressurized volume. You could send 50 or even 100 people on a single ship. You could send entire scientific research teams, engineers, construction crews. And because the cost per launch is so low, you could send multiple Starships during each launch window. Not one ship every 2 years, 10 ships, 20 ships. You're not establishing a tiny research outpost. You're building the foundation for an actual city. So let's talk about timelines because this is where catching the booster fundamentally changes the math. Before October 2024, SpaceX was still testing whether they could land Starship at all. They'd had several test flights where the booster either crashed or had to be deliberately destroyed. The upper stage had its own problems: heat shield tiles burning through, control surfaces failing. Every test revealed new issues that needed solving. The general consensus among space analysts was that crewed Mars missions were still 20 to 30 years away, maybe by the 2040s or 2050s, if everything went perfectly. But catching that booster changed the calculation. It proved the core concept works. The precision guidance systems work. The mechanical arms work. The structure can handle the forces. Now, it's not about whether it's possible. It's about optimization and scale. SpaceX is already building the infrastructure for high-cadence launches: multiple launch towers, booster production lines, propellant production facilities. They're moving from experimental test program to operational launch system. And here's the thing about exponential progress. It doesn't look like much at first, and then suddenly, it's everywhere. SpaceX went from their first successful Falcon 9 landing in 2015 to launching over 60 Falcon 9 missions in 2022, most of them on reused boosters. 7 years from proof of concept to operational dominance. If Starship follows a similar trajectory, we could see crewed Mars missions not in 30 years, but in 10, maybe less. The 2030s suddenly look achievable.
But Mars is just the beginning.
This isn't really about one planet. What we're witnessing is the moment space travel transitions from being impossibly expensive to being merely expensive. And that changes everything. With fully reusable starships, the moon becomes a construction site, not a destination. You can build permanent bases, mining operations, even propellant depots that make deep space missions easier. The asteroids suddenly become accessible. There are asteroids out there containing more platinum, rare earth elements, and precious metals than we've mined in all of human history. With cheap access to space, asteroid mining stops being science fiction and starts being a business opportunity. Space-based solar power becomes feasible, manufacturing in zero gravity, research stations throughout the solar system. This is the inflection point. For 60 years, since Yuri Gagarin first orbited Earth, space has been the domain of governments and their carefully selected astronauts. Expensive, exclusive, limited. But reusability breaks that model. When launch costs drop by 3 orders of magnitude, space stops being a place we visit and starts being a place we live and work. That booster being caught by mechanical arms on October 13, 2024, that wasn't just an engineering achievement. That was the moment humanity's future stopped being confined to one planet. The age of space colonization didn't begin with a grand speech or a historic first step. It began with a rocket coming home, ready to fly again.